So last week we talked about double integrals, setting them up. The primary motivation for the double integral was to generalize what we did with single integrals in area. So we bumped up the dimension. Instead of having a one-dimensional domain and a one-dimensional graph that would give us area, we had a two-dimensional domain and a two-dimensional graph that gave us volume. Okay, and so we had the sort of generic formula that volume. We could get the volume by doing a double integral over the base of the height dA, and depending on what plane we chose to project the solid into, the height could be in functions of z, functions of x, or functions of y. Okay. So what we're going to talk about today is double integrals using polar coordinates. So back in Calc 2 or AP Calc, whatever, sometimes you are working with a region in the plane, and if depending on what the region was, it just was plain easier to describe that region in terms of polar coordinates instead of the rectangular coordinates. So I posted a video from Calc 2 where we kind of go over polar coordinates again. Usually you see polar coordinates in your trig class or pre-calc class, but I'm assuming you've reviewed that, so we can jump right in here on the polar coordinate conversion here for double integrals. We've got the standard x and y conversions, which really come from, basically here's the picture that you can have in your head about this. You could have that, even though it's more general than this picture. That's sort of the picture you can have in your head that gets you all these conversions. X is our cosine theta, y is our sine theta. X squared plus y squared is r squared. The tangent of theta is y over x as long as x isn't 0. If x is 0, and you're sitting here on the y-axis, then you can adjust your theta to be, one of the pi over 2's. Okay. But let's think about, when we went and developed our double integral, the double integral we've been working on, we had a double integral over r f of x y dA. When we had this this region R in the plane, in the xy plane, when we chopped up the x's and we chopped up the y's, we got ourselves these little rectangles in here. Oops, I guess that. So delta x by delta y in there. And the area of that, the delta A, we just got by multiplying them together. Because that's how you find the area of a rectangle. Right? Or it was delta y delta x. And so then that's why our area differential, was either dx dy or dy dx. And then we would sample the points inside here, and we would figure out what the height was in terms of the function z equals f of x, y, and then we'd multiply, once again, the height times the area of the base, and that would give us our little volume element there. Okay. So let's see what we do, how this changes if I, instead of describing the region R in terms of rectangular coordinates, if I represent the region R in terms of polar coordinates. So we need to go back and do some geometry here. So say we got ourselves a circle of radius R. Try to make that a better circle here. So there's a circle of radius R. We're going to have an angle here, theta. And we'll say that theta is measured in radians. And we'll say we've got our radius R here. And if theta is measured in radians, and I want to figure out what the area of this sector is. So this would be a central sector because we're looking at the radius R back to the center here. What we can do is just use proportionality arguments. The area of the sector divided by the area of the whole circle is equal to the same proportion of how much I've swooped out, which in this case would be theta. And since we're measuring theta in radians, that's going to be divided by the radians of the whole circle. And so this gives me the formula that the area of a sector is going to be I've got the theta over 2 pi times the area of a circle. And the area of the circle is 1/2 pi r squared. Excuse me, pi r squared. And then we can go ahead and simplify this. The half is going to stick around. What's going to happen to the pi? That's going to cancel out. And then I've got my r squared theta. Once again, assuming theta is measured in radians. Okay, so that would be the area of a central sector. So the area of a sector is 1/2 r squared theta, assuming the theta is measured in radians, for that all to work out. Okay? So we've got a nice illustration here. Let's say we've got this this area described in polar coordinates. So this would look like we're looking at r's thetas, where the theta is described as sweeping between two angles alpha and beta, and r is described as sweeping between two numbers a and b. So in polar coordinates, r equal a, r equal b, those are circles, and theta is running from alpha to beta. So I've got my r here going from a to b, and then I got my theta then rotating that from alpha to beta, and that's going to sweep out that arc. So if I go in and do the same thing I did before with x's and y's and chop up the x's and chop up the y's, if I go in and chop up the r's, then I'm chopping up the radii. Okay, so this would be chopping things up in the r direction. And then if I chop up the angles, the thetas, I'm chopping things up in the angular direction, and I produce this grid this way. And so I get these little area elements here look like these little pieces of the wedge. So they're not circular sectors, they're part of a circular sector. Okay, so let's look at what's going on here. So we got the pi wedge here. Try to do this a little better. that, and it's missing this part. So if I call this, I'll just call this the outer radius, not the theta, just r out, and I'll call this r in, and I'll call this theta then. Then if I'm looking for the area of this part, what I can do is I can take the area of this whole wedge here and just subtract off the area of this little piece right here. So the blue area, the area here I want, that's going to be the area of the entire piece here, which we know is 1/2 the radius r out times theta minus the area of this piece here, 1/2 the inner radius squared times theta. So that's going to leave us with the area of the green part. And now we're just going to do a little bit of algebra here to simplify this. But do you see the geometry of this? Does this make sense? Taking the area of the big pi wedge minus the area of the little pi wedge. It's going to give us the area of that patch. So here's what we can do. Is I can factor out a 1/2 and I can factor out a theta. So I'm going to factor out the 1/2 out front. And factor out the theta out the back. And then I'm just going to factor this difference of squares. So this would be r out plus r in times r out minus r in. And let's take a look at this first factor. I'm taking the outer radius, the inner radius, adding them up and dividing by 2. So that's calculating the what of those two radii. That's our average. Okay, so we'll call that the average. So the average radius. And then, oops, I forgot my theta. R out minus R in, that's the delta R. And then times theta. Okay. So basically, if you take the average radius, it goes out to here. So that's your average radius. The theta is how far we're sweeping. And then the delta R is that piece right there. Okay, so you can also calculate it that way. So what that means in our little analysis here, our angle here, so this is going to be our average radius. That's what they're calling that. So our dA is going to be our average radius times our dr times our d theta. So there's our, well, I should do it this way. Our delta A would be our average radius times delta R times delta theta, because our angle here is delta theta. And as I make a finer and finer mesh, so that the areas of all these little things go to 0, then the R's are going to converge to whatever R we have at that given point. And then that becomes the dr, and then that's going to go your d theta. And so the long and short of it is, that's our area differential in polar coordinates, r dr d theta. Okay. Now to kind of take this back to something you might remember, you might remember the area formula back from Calc 2 or AP Calc was this. right? So you might remember this formula. And so if you took the partial derivative of this with respect to r, you can also get it that way too, however you want to do it. I like the geometric construction because it takes us back to that. And if depending on how you derive this, you probably derived this back in, well, if you had me for Calc 2, I know how you derived it. You went through the same sort of arguments we went through today. Okay, so that's the big theorem. If you've got your region R described in polar coordinates, then you can convert the integral to polar coordinates. Number one, you want to convert, you want to express R in terms of polar. So you wanted to express or describe R in polar. And then two, you want to take the integrand, which will be ostensibly in terms of x and y, and then convert that to polar using the conversions. Okay. But I can't stress this enough. In order to get the limits of the integral, you need to express your polar, your region in polar coordinates. You can't just look at these things and convert these individual things to polar coordinates. It doesn't work. Okay? You have to express the region in polar. You got to think in polar. And then for the integrand itself, you can convert that over from x's and y's to r's and thetas. Okay. All right, so here we go. Example 1, convert the following integral from rectangular coordinates to polar coordinates to evaluate. So this is like the first question on your test this week is going to be one of these. I give you the integral in rectangular. You got to convert it over to polar. So the first thing I recommend you do is sketch that region R and then describe it in terms of polar coordinates. So if I look at how they've set this up here for us, the outermost integral here is on x. X is going from a constant 0 to a constant 1. So there's my x. So I'm chopping the x-axis up from 0 to 1. And for a constant x, let's look at what the y is running between. So y is going from x root 3 up to the square root of 4 minus x squared. So if I look at x root 3, that starts at 0 here and goes up to root 3. That's a line. Y equals 4 minus x squared. Do you recognize what that is? What kind of shape is y equal square root? That's a semicircle, yeah. It's the upper half of a semicircle with a radius of 2. So when x is 0, y is 2. When x is 1, y is square root 3. So they do match up. So here we go. Boom. So here's our region R. Right? For a fixed x between 0 and 1, the y is sweeping from there to there. And look at that. It's the central sector of a circle centered at the origin. So this thing has polar coordinates written all over it. So now I got to figure out how to describe this in terms of polar coordinates. So let's go and look and see what's going on here. If I look at y equals the square root of 4 minus x squared, convert that into polar, that's a circle of radius 2. So you convert that into polar, what would you get? That's just your r equals 2, good. And then for the y equals x root 3, which would be this down here, that's a line through the origin, so that's going to be a constant theta. And what would the theta there be? So you can think of this as y over x being root 3. So that would be your tangent. So what angle has a tangent of root 3? So that's your pi over 3. So that's your theta equals pi over 3. And then, what's this theta here? So theta is pi over 3, that's this line. And I'm rotating around, and I stop here at the positive y-axis. That's the x equals 0 part. What's this theta? So theta is going to go from pi over 3 to, pi over 2. And then the r is going to go from the origin here to r equals 2. So even though this looks like just a pi wedge to us, in rectangular coordinates, we've got constant bounds. So it's kind of like a polar rectangle. It's going to manifest itself as this wedge. So the long and short of it is, for my region R, it's described as theta going from pi over 3 to pi over 2, and then r going from 0 to 2. Are there any questions on how we obtained that description? Okay. All right, now for number 2, we look at the double integral as given to us. We've got the integral 0 to 1, x root 3 to 4 minus x squared. We got this. And you can only imagine the sort of fun you would have, air quotes fun you would have, trying to evaluate this as written. Okay, ostensibly you'd have to pull out some trig subs and other sorts of assorted nonsense for this. But we don't need to, because we're going to move over to the land of polar coordinates. Now this is our dA in rectangular. So in polar coordinates, the dA, it's not just dr d theta, but it's what? Don't forget the factor of r. So if there's a common mistake, it's students forget that extra factor of r. And now let's go in here and simplify things. This region, we're describing this region. Theta runs from a constant pi over 3 to pi over 2. And then for a constant angle theta, the r is running from the origin, which is r equals 0, out to r equals 2. So once again, if you haven't watched the video where I go through how the graphing and stuff in polar, I recommend you do that. That'll help you visualize how this area gets swept out. And then we have to convert the integrand. I've got the square root of x squared plus y squared, so that's going to be the square root of r squared. And usually the square root of r squared, that would be the absolute value of r. But in our particular case, r goes from 0 to 2. So do I really need those absolute values? Nope. So I'm just going to have an r squared in there. So my integral is going to be the integral from pi over 3 to pi over 2 of the integral from 0 to 2. I've got r here from simplifying the integrand, and now I'm going to multiply by the other r, so that's an r squared, dr d theta. And we're in a situation we were in last week where this integral here has nothing to do with theta. There's no thetas in the integrand, there's no thetas in the limits of the integral, which means I can actually factor this whole integral out. And I can write this as the product of two integrals. And so the first integral, we're just going to be we're getting pi over 2 minus pi over 3. And then the second integral, you would just integrate that as usual. You'd get your 1/3 r cubed. plug in the 2, plug in the 0. And so this would be what? 3 pi over 6 to pi over 6, pi over, what, 24? No, 48. I'm sorry, not 1/8. Be 8, 8/3. Thank you. Yep, so this would be 8/3, and then this would be pi over 6. So what, 4 pi over 9? We don't know what the integral was calculating. We don't know if it's a volume or something else. We just get the numerical value. But you can see how much simpler this is if you take the time to convert, to recognize it's a good area, good region for polar, convert it over to polar. Computationally, this finished it up a lot easier than if you try to do it the other way. Okay, just it's much easier to do. Right, example 2, find the volume of the solid bounded by the paraboloid z equals 4 minus x squared minus y squared and the xy plane. So we got a little sketch of it here. Volume, remember, our generic formula for volume is a double integral over the base of the height dA. And so if I look at here, we've got z equals 4 minus x squared minus y squared. And we've got the xy plane. But what's the equation for the xy plane? That's just z equals 0. And so if I want to project this into the xy plane, I can, substitute here z. And I can get x squared plus y squared is 4. And by golly, x squared plus y squared plus 4 is a what? That's a circle centered at the origin with a radius of 2. Which means, here we go, there it is. Now, as far as the base of the solid is concerned, do I want the inside of the circle or the outside of the circle? You want the inside. Okay. And once again, you might be able to pick that up from here, or we could always head over into GeoGebra. Let's see how well behaved GeoGebra is today. It's taken a while to boot up. That's not a good sign. So you can use GeoGebra or Desmos. The GeoGebra will actually show you the intersection of the surfaces. So we got z equals 0 there. Z equals 4 minus x squared minus y squared. There it is. And remember, if you go over to the Tools menu, intersect surfaces, click on that, and then click on the two surfaces there. And there it is. Okay, that's going to be the base. So put the base in the xy plane, but we're going to describe that using polar coordinates. All right. So once again, volume, integral over the base of the height dA. So the base is going to be in the xy plane, but it's going to be in polar coordinates. So if I look at my region here in polar coordinates, we've got x squared plus y squared is 4. What's the equation of that in polar coordinates? That's just your r equals 2. Now if I want to sweep out the inside of this circle, I would start here at the origin, out. So in the origin, that's r equals 0 to 2. And then for a fixed r, how am I spinning the theta? So if I pick a fixed r, theta spins from 0 to 2 pi. So once again, this circle is actually constant bounds. All right, so that's gonna help me with my base. Now I got to figure out the height. So if the base is in the xy plane, I'm using what variable for the height? The z. So height's going to be in terms of z. So I'm going to have to take the top surface minus the bottom surface. So you can see in a little sketch here, what's the top? That's the what? That's the paraboloid. Yeah, 4 minus x squared minus y squared. And the bottom is the xy plane, but that's aka z equals 0. Okay. But I need to turn this into polar. And so what would this be in terms of polar? Yeah, 4 minus r squared. Good. Okay. So once again, if you haven't, if you need some brushing up on the polar coordinate stuff, there's a video and a handout up there for you to work through. But now we're good to go, because our volume is going to be double integral. And remember, for the area differential for polar coordinates, it's not just the r d theta, but what? There's that extra factor of r. We've got 4 minus r squared. And the region as set up, theta goes 0 to 2 pi. R went from 0 to 2. There it is. Okay. And as we saw earlier, notice that the inside integral has nothing to do with theta. There's no thetas in the limits of the integral. There's no thetas in the integrand. So I can actually write this as the product of these two things. What would be your first step to evaluate the r integral here? I guess you could do u sub. I was just going to multiply it out. Either way will get you to the right. You could let u be what's in parentheses and move it around. This integral out front, once again, we've got this, just like in the first example, the region has theta symmetry, and the integrand has theta symmetry. So if I think about this solid, it's completely symmetric in terms of thetas. So essentially what I'm just doing, well, we'll talk about this more next week when we get into cylindrical coordinates, but this is just going to multiply by 2 pi. I'm essentially just, for a fixed theta, if I fix the theta there and I slice this, I'm essentially just finding the area of that and then spinning it around by 2 pi. That's kind of what's going on there with the integral. Then you go through however you want to do it, u sub, whatever you want. It's all good. You'd get your 2r squared minus 1/4 r to the 4th. That would give you 8 minus 4. So you get 8 pi. And since this was a volume calculation, we would write units cubed here. There it is. Okay. And once again, you can compare if you had to set this up. There's a lot of symmetry you can exploit as well. So for example, you could just have theta run from 0 to pi over 2 and then multiply your final answer by 4. All of these things are available to you. But since we're first starting this stuff, I'll let you play around with these things and make those observations. I don't want to do too much too quick. Okay. Any questions on setting this up? We're still using this, the integral of the base of the height dA. That's still our volume formula. We go to find the base. Looks good in polar. That's the new thing. Describe it in polar coordinates. So don't waste your time. You can just set it up in polar right away. There you go. All right, find the volume of the solid between these two surfaces. So we got a couple surfaces here. We got the z equals square root 18 minus x squared minus y squared. Anyone recognize that? What that is? From week 2. It's been a while. That's actually a sphere. Yeah. Yep. So that's the spherical cap. And you recognize this? That's a hemisphere. And this is going to be a what? That's a cone. This is like one of those snow cones you would get. Right? Which last week we probably could have used a snow cone, but not this week. This week nature will provide us with the snow cone, depending on what weather model you look at. So what the volume of the solid between these surfaces? Once again, it's described as being between two functions of z. So we'll use volume integral over the base, height, dA. The shadow here suggests it's going to be a circle, which that's what gets us in the door with polar coordinates. So if we make the base the xy plane, then the height would be the z. And if we're thinking polar anyway, let me run this by you. If we're going to do the base in the xy plane and have the z as height, we're going to end up setting these two equations equal to each other anyway. Since we're going to be going to polar, we may as well just convert to polar here. Does that make sense or not? In other words, if we're thinking polar, what would this equation be in terms of polar? And then this would be here. You with me or not? So now I could get rid of those square roots by doing what to both sides? Squaring them. So I get 18 minus r squared equals r squared. So what would r squared be? That would just be 9. So I could take r to be what then? Yeah, 3. And once again, we're going to be inside or outside the circle? Yeah. And so once again, if, I invite you to make good use of, we got this nice tool here. There's your hemisphere. There it is. Not sure why the intersect tool is being silly, but you can see it right there. There's that circle. Right. So here's the solid, there's where they intersect, so it's going to be a circle. Okay. So now we're good to go. Our base intersect. Well, let's try. See, now it's frozen. Oh, there we go. Object. Okay. Yeah, I'll have to look at that. Yeah. Sometimes it just gets click, click, click. Ah. Read. Oh, it didn't like that. That could be. I don't know. Sometimes, yeah, sometimes it gets extra finicky, but on that one you can kind of see the circle regardless. Anyway, let's figure out what this looks like. Once again, we've got a circle centered at the origin with a radius of 3. So the R is going to start at the origin and go out to 3. And then the theta is going to be here to spin this around. So you get the entire circle. And so the height, once again, that's the Z. Going to be top minus bottom. And we already converted these equations over using polar coordinates. The top is the hemisphere, the bottom is the cone. We got that. Now we'll set all this up for our integral. So the volume is going to be double integral of the height over the base. Once again, don't forget, it's not just the r d theta. Don't forget that extra r. We got the square root of 18 minus r squared minus square root of r squared. We'll deal with him in a minute. R is going from 0 to 3. Theta is going from 0 to 2 pi. And once again, the square root of r squared, that's the absolute value of r. But look at r, it's always positive, or always bigger than or equal to 0, I should say. So I can simplify that to r. So I would have square root of 18 minus r squared minus r dr d theta. Once again, we can split this into factors because the inside has nothing to do with the theta. The object we're looking at has theta symmetry to it. And then to start integrating here, you'd probably want to distribute there. And then on this one, for sure, you'd probably want to do what for this first piece? Yeah, you'd probably want to do a U sub on that for sure. And then you can integrate him as is. Okay? So once again, we've got this theta symmetry. And so the theta integral just pulls out. And I point this out now because a few years ago, by a few I mean it could be as many as 10 at this point, one of my students went off to do PChem and came back. And apparently in PChem they do this all the time. A lot of their wave functions are symmetric with the angles, so they just split things up into factors. They just teach them that's how they do double integrals. Because this, it was funny, the prerequisite for the PChem they were taking was only Calc 2. They didn't even have any multivariable, so they just did the integrals this way. They just had them split it all the time. And my student was like, well, but can you always do that? Well, for the ones we're doing. They were always running stuff off to infinity anyway. So anyhow, you go through all that. You're going to get this 36 pi root 2 minus 1 cubic units. Okay, so you can check that going through your machinations. And remember, Desmos will do double integrals. We demonstrated that last week. So as you're working through your take-home, on the first page on your take-home, you got those 3 different double integrals. You can verify that at least they work out to the same number on Desmos.